Panikya. I'm a master's student at the Faculty of Industrial Design Engineering at TUF. And my co-author, Dr. Ton Huysmans, is an assistant professor here. And the topic of my presentation is the comfort of aircraft seats for customers of size using digital human models and virtual reality. This research was performed as a part of my master's education here at TUF. Maybe first of all, it's good to show you the problem I'm assessing through VR. I'd like to pose you this question first, like why do we have these situations in the airplanes even when the design is so advanced? Most of you must have had this experienced similar situations, especially the fight for shoulder space with co-passengers or the notorious middle seat. Uh, or the agony of forgetting to choose a seat and then ending up getting a middle seat. No matter what your body size is, you must have had some space crunch situations like this. Here, I'll be using this term customers or people of size to refer to the population which is having the BMI above 30. Now, imagine the previous situation which I showed in the previous slide from the experience of a person of size. Be it the airplanes or the amusement parks, the seats are a cause of anxiety and embarrassment for these people of size. And for most of such population, their body size is not a choice. For some of them, it can be due to genetics or some can be due to health conditions. Yet they have to suffer humiliation and prejudices everywhere. There has been several blogs and articles mentioning about the people's embarrassing situations in flight journey due to their body size. Some have been asked to deboard the plane, some have been complained about by the co-passengers. As designers, we have to ask ourselves, like, where exactly lies the problem? When designing a product, usually designers take a range of population to fit in their design, but these people of size usually fall outside that range. So because of that, they face a lot of consequences. Such seats are designed in a way of one size fits all, and it is sure to cause disappointment for a lot of people if they're doing so. And to make it even more difficult for them, the airline policies for different carriers are varying, and they change frequently, and it offers little consistency. So here, the aim of this research is to enable sufficient insights for the designers into the situation of the customers of size during the design process. The digital human models and virtual environments hold a lot of benefits for this, such as seeing the world from the different person's point of view. So the designers can use this technique to see the perspective of their target group. In the early design stages, this gives an alternate method of design assessment than building expensive and time-consuming prototypes. It is much easier to assess and rectify problems that may arise at a later stage. Plus, we can assess the products in real size than using physical models. Currently, there are a lot of applications where these techniques have been used, such as virtual manufacturing maintenance. Virtual manufacturing can analyze future manufacturing process to ensure the optimization of product design quality and maximization of production efficiencies. Currently, Ford and John Deere are using virtual reality to assess the ergonomics of the workers during the assembly stage. Ford in 2015 reported that they will be using VR and motion capture suits to refine the future production lines. And John Deere uses virtual reality in the design process to understand and optimize both how future operators will use its machines and how employees will assemble them. They run these virtual programs and let the experts see from the worker's perspective to understand the critical operations for workers. The maintenance personnel can do maintainability analysis such as visibility, reachability, maintenance pace, and ergonomic evaluation in the virtual environment. So here in this research, I have applied this technique to assess the comfort of the economy class airplane seats from the perspective of a person of size. It is not only an immersion into this virtual environment, but also immersing the viewer into the body of a person of size. So for this study, I have selected the population to be the Dutch male and female, aged 18 to 66 years. And the data was retrieved from the CSER data available from the DINET database. And according to the data from the Seat Guru website, I took the seat dimensions of the KLM economy class. It came out around to be 17.5 inches is the seat width, and the armrest width is 2 inches. And the data corresponding to this economy class seat is corresponding to KLM Airbus A330 model. And in this chart here, you can see that the gray area is the discomfort zone, and a considerable amount of population is in lying in that area. It's around 10.5% in that uncomfortable area. And when you take the case of a hip breadth, it's worse. It's even worse. It's like the seat width being 17.5, which should include the hip breadth as well as the clothing allowance, which is around 1 inches. So here, around 28% of the population lie in the uncomfortable zone, which is shown in the gray area, and the squeeze with fit range is above that. This shows that a significant amount of population has been neglected in the seat sizing. So the major comfort influencing dimensions considered here for covering the obese body sizes are BMI and shoulder breadth. Two mannequins were selected based on these two ranging a P95 and a P99. Mannequin 1 was a P95 BMI and P99 shoulder breadth, and mannequin 2 was the other way around. So in order to create the virtual simulation, I had used Unity here. Before the mannequins were exported into Unity, I had to do some. The mannequins were exported from the Dynet website and had to be scaled and processed in Blender. It was then rigged online using a software called Mixamo. And then after a few texture editing and stuff were done, it was imported into Unity. These are the equipment used for the experiment: the HTC Vive headset and perception neuron motion capture suits, which had a 32-point sensor tracking the whole body movement. These two equipment were integrated into Unity using their respective plugins. And also the main part of the modeling was the interior of the KLM Airbus A330 model, which was done through the help of a freelance modeler. And this is how it looked like after the equipment was set up. Although this is how the participants felt like when they were doing the user test. So one good thing about this research was that there was no difficulty in getting the participants. It was like only one person had to be called up and the rest would just send in their friends. So the user test performed was on 8 participants, 5 male and 3 females. They were asked to sit on a physical chair and see around the virtual environment. They were asked a few questions to rate about the comfort, seat width, and the leg space. They perform the same question in 4 test configurations as I have shown here. So there'll be 2 tests using each of mannequins, and one of the tests will be in the sitting in the aisle seat, and the other experiment would be sitting in the middle seat with co-passengers in the left and right. The test order was also interchanged for the half of the participants to remove any order bias. So here I'll share you a short video clip to show you how the experiment was performed. I hope it is visible. Yeah, that was it. So that was how the users were asked to see around, and they were asked to see whether they are feeling good sitting in that seat or whether they are squeezing into the seat. So yeah, the participants agreed that they felt like they were seeing through the eyes of a different person, even though the quality of the environment was very much scaled down. It did not feel them a fully intuitive feeling, but it was good for them to assess the visual comfort. All the participants I had selected were of normal BMI range, and they felt bulkier and taller in that virtual world. The seat width and comfort of sitting for long hours was given negative ratings by the participants. But strangely, they felt the leg space was not much of a problem. You could see here in the chart I have shown that the ratings provided by 8 of the participants on few of the questions. And most of them mentioned that the armrest width and sitting for long hours in such a seat are very uncomfortable for them. This research shows an effective and easy way to have a visual assessment of the design. It offers a low-cost prototyping techniques, early stage product assessment, and most of all, enabling the designer to see through the eyes of their target population. Although the research has shown a lot of future paths, it did have some limitations. The participants who were involved in the study was all from a normal BMI range. It could have been a good option to have a study involving participants with BMI greater than 30 so that the ratings can be compared with the normal BMI participants. Also, the motion tracking equipment was a little buggy and every time needed adjustment to calibrate its position in the 3D environment. So the study was only a visual immersion in the virtual world. Future studies could think of how to improve the immersive experience combining haptics, auditory, and other senses. For future applications of this research, it can be beneficial for the fashion industry, automobile interior design, etc. That's all about my research. I would like to give the time for some questions and feedback. Also, you could contact me and contact me via mail or LinkedIn. Thank you.
Okay, thanks very much, Sarat. So I turn to the audience. Are there any questions? Yeah, please raise your hand or you can also type it in the chat. I see no questions, I think. Maybe one short question. I was just curious, what would be the effect of interaction in such a simulation? As far as I can see, it's mostly static, these characters. Whether they have more movement and interaction, how would that affect the simulations and the results?
The interactions, you mean between the co-passengers or with the environment?
Mainly passengers, but also the environment, because in a plane, the characters are not static, right? You move all the time to the left, right? And that can also have an effect on that type of simulations, increasing the realism of the simulations. So what are your thoughts about that?
The interaction between the co-passengers could have been nice, but in this simulation, I have used only the live person was the only one, the user, the participant. The rest of them were just dummies kept onto the nearby seats. It could have been nice if they could test out between multiple participants whether they feel the shoulder shrugging or something while sitting down. And the interaction with maybe pressing the buttons or adjusting something if they can reach it. That could have been a nice interaction. Yes.
Okay, any other questions? And yeah, if no more questions, I think there is room for questions and chatting later as well. I would like to thank Sarat as well. And we move to the last presentation of the session today from Alicia Bohars.
Yes. Is there a strict time limitation? Like, does the room close?
I think we can a little bit exceed like 5 minutes, but not so long.
I'll try to rush a tiny bit.
Yes. So, yeah, take your time, but we can exit a little bit, I think. So Alicia is a master's student from Utrecht University, and her work is supervised by me and our colleague Anja Volk.
Yes. So hey, I'm Alicia Bogaars. I will be presenting a paper called Music-Driven Animation Generation of Expressive Musical Gestures, which is also what I did my master thesis on. So I'll first give a quick overview. So of course, I'll go over the introduction, a bit about the background, related work. I'll go over the methods I used, show the results, of course. Then I conclude everything I said in the presentation. And I give some limitations I had with the project and any options for future work. So the original goal of this project was to create a 3D musician that moves expressively to a live MIDI input while using deep learning methods. The idea of this project came from an organization called My Breath, My Music. What they do is they provide special MIDI instruments to physically disabled musicians that do not require a lot of movement to be played, so they can express themselves through music with this. And the purpose of this 3D avatar would be to accompany them on stage, and it would move to the music they are playing, so they can express themselves physically as well through this avatar. However, when I started to look into generating expressive musical gestures, I saw that this field was relatively unexplored. I saw that there were many studies, of course, that focused on generating playing animations, but these are mostly focused on generating the correct fingering positions for keys on a piano or strings on a guitar. There was really only a small amount of studies that also involved the rest of the body playing expressively. On top of that, there were also no studies using MIDI, so I had to shift the scope a bit and make the new goal to find out how to generate believable, expressive musical gestures from an audio input. So first, of course, I have to explain what expressive musical gestures are. Musical gestures, as a term, it envelops every gesture that a musician makes during a performance, so playing, but also nodding to another performer on the stage to, for example, indicate that they're going to play the next part. And the expressive musical gestures that I wanted to generate are also called auxiliary gestures, and they are all the gestures that are not involved with playing music. So I have some examples here. On the left, you have the saxophone player, and you see him moving his upper body, bending down a bit to the music. And these gestures are not needed to play the instrument at all. These are just made out of like the need to express themselves. The same goes for the pianist on the right. You can see his head moves. This is also not needed to play the instrument, but he does it voluntarily to express himself. So because there was not a lot of research, I had to dive into several fields in order to get some inspiration for the methods that I had to use. So first of all, I started to look at music cognition studies, which actually studied how music features affected the gestures that musicians made in performance, like for real musicians. And from that, I found that there was actually no conclusive answer yet on what caused these expressive musical gestures. However, there were a few important features that affect the gestures when they were made, or how big they were, or if they went up or down. And these were the melody, or the change of the pitch of the music, the rhythm of the music, and the dynamics or the loudness of the music. However, even after finding these features, they still stated that music to motion mapping is not one-to-one. For example, different musicians will produce different gestures that are unique to themselves. The same musician will, over a period of time, change the gestures they make as they become more familiar with the music that they are playing. And of course, all of the gestures are voluntary actions. Musician can just decide not to use them and still play the same part of music. So this is a kind of difficulty that is there. Of course, I can't just look at this and dive into the deep learning part. I had to look at how people actually extract these kinds of features from audio. So first of all, I started to look into audio-driven expressive motion animation. In this case, they don't use music, but they used speech to generate expressive facial animation or conversational gestures. And I saw that using mel frequency septal coefficients, or MFCC features, were relatively common for this. So I think the simplest way I could explain this feature is basically the computer version of audio as we hear it. And this feature was often described as the pitch of the speech audio that was given in. And instead of MFCC, sometimes also the F0 trajectory was used to describe the pitch. And this is basically a sort of melody extraction algorithm. So in this case, it just denotes the frequency or the pitch in which the voice is speaking at that moment. And for one study, I also found that the dynamics were used, so the loudness of the music or loudness of the speech. And this was extracted through the energy level of the audio. I did mention that there were a few studies that focused on generating expressive motion to music. One of these was actually procedural animation, so they didn't use deep learning. They had predefined gestures, and these were steered by musical features that were used as input. In this case, they also used dynamics, so loudness, and they used the beats to kind of steer when a gesture would happen. So the beats kind of relate in rhythm in this case. And there was one deep learning study that did focus on generating expressive playing. They also mainly focused on the arms, but they took the upper body into account as well as to make the character look more expressive. So I counted this as expressive gesture as well. And in this case, they also used MFCC features for the pitch and the log mean energy also to denote the dynamics. And because there was only such a small group of studies on music-driven animation for expressive musical gestures, I also looked at using music to generate expressive dance animation. And I found that in this field, actually, it was quite common to use multiple features at once. And they actually stated that the more features you use, the more realistic a character will move to music. So here again, I found that pitch and dynamics were again used with the same features, but also rhythm was very prominent here. And they used the location of the beats as an input to make the network align certain gestures to the music better. And they said that adding this info actually made it look more realistic, as gestures, of course, would occur to beats, as humans, when moving to music, naturally would do as well. So this led to the following research questions, which were: can we generate believable expressive musical gestures using the musical features from audio input? And which musical features do we need to generate these gestures? So of course, before we can do any of this, we needed a data set. So we used a public data set, which is called Datasets for the Analysis of Expressive Musical Gestures. This data set contains motion capture and align audio recordings of a pianist playing the same song excerpt, but in different tempos of the same song. So in this case, we had the categories fast, normal, slow, and rubato, which is a free-form choice of how fast or how slow to play a piece. So I have two examples. On the left, there's fast. So you can see that's pretty fast. And then on the right, there's rubato, which is the free-form. And you can see that these contain different motions between them. So this was something that we needed in order to see if the network could generate different gestures for these inputs. So for the features, I extracted the ones that I mentioned before. So the MFCCs, the F0, the beat onsets, and the energy levels. I decided to split the MFCCs from the pitch. This is because in music, MFCCs contain a lot of, implicit sounds. If you can imagine a pop song in your head, then MFCCs would contain everything: the vocals, the background music, drums. Well, the pitch would, or the F0 in this case, would just take out the vocal melody. So there's a lot more info in just MFCCs, and that's why I thought it would not be fair to list it under pitch in this case. To extract these features, I used Librosa for everything but the F0. For F0, I used Melodia, which was also used in other researches. For the model, I used the long short-term memory network. This is quite common to use for long-term time series predictions, and it was also used in the one music-driven gesture research, and it was also used in the dance animation research. So I thought this was a reliable choice. As input, you use different combinations of features to find which set work the best. And we use the online training method, which means that we train on a slice of input at a time, and then use the generated input back into the network to generate the next input. Additional to the music features, we also put back the positions of the body of the previous frame, or if you generate the frame, we put that into the next step. And the velocity, so the change in motion between the current and the next frame. For our objective analysis, we measure different parameters. First of all, we check the training performance using the mean square error during training. When the gestures were generated, we use the average positioning error, which is basically the error between the generated results and the ground truth for every body part at every frame, and then the average over that. And then we also check the smoothness parameters, which are called the acceleration and jerk. Basically, where these are for are to see if the animation looks natural. This is because, for example, if you have the very fast song, you want the character to be playing the piano and doing the gestures fast as well. So these parameters should be similar to the ground truth in order for it to appear more natural. So when we looked at the accuracy, we saw definitely that MFCC scored the best. Using the musical features on their own did not really give a good result. You can see it on the left when we just use pitch. Character was very wobbly. There's not really defined gestures there. However, when we use all of the features together, gestures are more defined. And yeah, it moves a bit less wobbly. Well, MFCC did score the best using all of the features together, which is the MFCC and the pitch, rhythm, and dynamics. Using all of them together was not significantly worse than MFCC. So these two kind of scored the best together. However, when we looked at the smoothness parameters, using all of the features together was significantly better than MFCC in terms of how natural it made it look. No, I need to play this other one first. When you look at the MFCC, the gestures are a bit jagged and they kind of delay after the ground truth, which is the like a bit see-through one in the background. However, when we use all of them together, the gestures were more timed and followed the ground truth a bit more with regards to timing. We used the alt condition to do a user study as well. In this case, we asked about the believability and the smoothness of the animation. What we did in this user study, we had both the ground truth animations and the generated animations. And we just showed them in a random order. And for each animation, asked whether the motion of the character looked to be in line with the audio and whether the motion of the character looked natural or smooth. In addition to all the normal demographic questions, we also asked whether participants were familiar with piano performances, because I thought there would be maybe an interesting difference there if they happen to see a lot of piano performances in their life already. So when we went to the believability results, we saw that we had good results for fast and normal tempo. However, the model performs worse than the ground truth for slow and rubato, which are generally longer sequences. And of course, notes might take multiple slices before they end or they shift to the next note compared to fast or normal. And comments from the participants were that the character looked to be playing stiffly and that there was a lack of motion in the arms. We also saw that the people that were familiar with piano performances actually had a stronger opinion, which means that they had significantly different results between the generated and the ground truth, whether they were good or bad. So that was also interesting to see that they were a bit more critical there. When we looked at the smoothness, we saw that the results for fast and normal were okay for the unfamiliar people, so the people that were unfamiliar with piano performances. They didn't really see a big difference. However, when we went to look at the participants that were familiar with piano performances, we saw that they generally had more negative opinions about the generated results when we asked whether it looked natural or not. They also said in comments that the transitions between gestures wasn't smooth, that the movements were too small, and that the character did not appear to correctly convey the emotion. So quick roundup. First of all, the goal was to generate musical gestures from music input. We looked at different fields to find which features to use. We used the LSTM network to generate gestures using motion capture input. The research questions were if we can generate believable expressive musical gestures using musical features from audio input, to which the answer is yes, but of course they can still be improved, especially for the people that were familiar with piano performances, because they were not very convinced yet. And what musical features are needed? Well, we saw that MFCC by its own already gives very good results. However, adding more features increases the believability of the generated animations. And this is also what's in line with what was said in the music-driven dance animation, where more features equals to more realism, basically. So of course there are some limitations. The network might have been too simple for long sequences or to handle these long sequences, which is why it performed worse for these. And of course, you could use way more training data, as it currently cannot generalize over other songs except for this song excerpt. So of course, there are options for future work as well. First of all, of course, expand the data set, add more styles, songs, instruments, players, in order to generalize better over different performances. We need to improve the model architecture so it works better with different sequences. We can use other features because the music-driven dance animation still used different features such as the structural music information, such as saying when a chorus or a verse starts. And of course, the model has to be adapted for MIDI file input to work with the instruments, and the model has to work in real time as well. So I included some links, just if you're interested. The paper was published as a late-breaking results paper in ICMI 2020, and I have the video presentation from that conference here, website, like simply detailing what we did, and the research poster of that conference is here as well. But yeah, that rounds presentation up. So thank you for listening.
Okay, great. Thanks a lot, Alicia. I think there was a little bit of a delay between the slides, at least on my side. I'm not sure how was it for the other audience, yeah. So are there any questions? Please raise your hand, or you can also write it in the chat. Of course, myself, I know this work for quite some time, so I don't have too many questions about it anymore. So Alicia successfully defended her thesis last week. Yeah, it was a work that was leading to a nice publication as well. So proud of that. I think if there is no more questions, that is it for the first session. And if there are more questions raising, you can still write it in the chat.
There's one that just came in the chat. Maybe
okay.
we can.
Yes. From Faraz Yanan. Is there a good library to combine DL with virtual reality toolkit?
I'm not sure if this one is for me. I think it's for the previous presenter, maybe.
Faraz, maybe can you ask it yourself, or that's is it for Alicia or a previous?
Yeah, can you hear me now?
Yes.
Yes.
Yeah. So Alicia, you have used deep learning to basically combine, I mean, your model with a virtual avatar, and I was wondering if there is a good library that is available to combine deep learning with the virtual reality toolkit, or maybe with a mixed reality toolkit or something similar.
I'm not sure about this. Basically, what I did is I pre-generated the results and then wrote a script to animate it. So I kind of disconnected these two parts.
So yeah, it's not a real-time thing. I mean, basically the processing happened offline.
Yeah.
Okay.
But I think someone linked
yes,
a library.
Yes, machine learning agents. I think, and Helen has a short question. She said maybe.
Yeah, thank you for the presentation. I have a very short question. So I'm not specialist of deep learning. I have a question on the user study. I was wondering in the results, or in the design, how do you make the choice of the point of view? Because depending on the motion, maybe you can see more difference or similarities depending on the way you observe the.
Yeah, I made different point of views actually, and I asked Zarin and model supervisor which one was the best actually. So that was kind of the critics on that.
Okay, so I guess that answers the question. We are, I think almost closing this session. I would say that, because there is a keynote already starting as part of the conference, we can stop the recording already. and this room can stay alive if people want to continue the discussions. Maybe Wouter, we can already stop that.
The keynote is supposed to start at 3:45, so if you really want to see the beginning, you're still on time to make the switch, but you should probably do it soon.
Yes. So I would like to thank all the presenters and all the speakers and our audience for their questions. And we will continue after the keynote for the second part of the workshop that will be chaired by Wouter van Tol. Okay, so thanks for your participation, and we will see each other at 5:30 again.
Thanks.
See you later.
See you.
See you.